And we've arrived at the heart of dynamics, the single most important equation of the year, N2L, Newton's second law, the biggest of all kahunas. We've been looking at forces, which are interactions between objects, and we've learned that forces cause acceleration. Newton's first law of motion, N1L, also known as the law of equilibrium, that told us what happens if the net force on an object is zero. We had static equilibrium and dynamic equilibrium. The object does not accelerate. Newton's second law tells us what happens if the net force is not zero, if there is a net force. In other words, if an object does accelerate. Newton's second law tells us how to calculate the acceleration of an object. And it comes from these two principles we've discussed so far, observational principles. One, forces cause acceleration. They are the cause. And then principle two, mass, this property of matter, resists acceleration. Mass, that measurement of an object's inertia, the resistance to acceleration. So we've got forces causing it and mass resisting it. If force causes acceleration, then we say that force and acceleration are directly proportional to each other. If y and x are directly proportional, that means as x increases, y increases, and as x decreases, y decreases. The graph would be linear with a y-intercept of 0 right here. That's a directly proportional relationship between y and x. K here just represents some constant. In this case, it would be the slope of this line. So if two quantities are directly proportional, then they obey an equation like this. Y equals some constant times x. That's the relationship between force, which would be like x here, causing acceleration, which would be like y here. Now, mass resisting acceleration, that's what we would call an inverse proportionality. They are in mass and acceleration inversely proportional. For a given force, as the mass of an object gets greater, the acceleration of it would be less, because the mass is resisting the acceleration. Likewise, for a smaller mass, you would get a greater acceleration. And so the graph of y versus x, if they're inversely proportional, would be a curve something like this. And so here, mass would be playing the role of x, and then acceleration, the outcome, would be y. So putting together this directly proportional relationship between force and acceleration and this inversely proportional relationship between mass and acceleration, we can propose Newton's second law. Acceleration must be directly proportional to net force that's causing the acceleration and inversely proportional to mass down here in the denominator, resisting acceleration. As the net force gets bigger, acceleration gets bigger. But as mass gets bigger, acceleration gets smaller. And there it is. This competition between the net force, the thing that is causing the acceleration of the object, the interactions it's experiencing, and the object's mass, which is resisting that acceleration. This competition determines what the acceleration of the object will be at that instant. Here it is, Newton's second law. We can learn something about the units from the SI units from looking at this equation here. Acceleration we measure in meters per second squared, forces in newtons, and mass in kilograms. So what this equation tells us is that a newton divided by a kilogram is equal to a meter per second squared. You can convert between units using Newton's second law. Okay, let's see. If we've got an equation like this that looks actually like a scalar multiplication of a vector. If b is some vector that comes from multiplying another vector by a scalar, then we have this set of relationships. But that's exactly what kind of equation Newton's second law looks like. Here, a is a vector. It equals 1 over the mass, a scalar, because mass is a scalar, it's just a number, times this other vector, the net force. So, in fact, we have a scalar multiplication going on here. What this implies is that, of course, the acceleration of the object will be parallel to its net force. That we already know, because at every instant, an object accelerates. Parallel net force. And it also tells us that we can break Newton's second law into two components here. This says that the x component of acceleration is 1 over mass times the x component of the net force. And the y component of acceleration is 1 over mass times the y component of the net force. And likewise, the magnitude of the acceleration is 1 over mass times the magnitude of the net force. So very often we'll be using Newton's second law in this component form. We want to find the x component of acceleration. We sum the x components of the force and divide by mass. Likewise for the y components of the acceleration. You may have often seen Newton's second law written like this: F equals ma. Really, that's the way it's most commonly expressed. But writing Newton's second law in this form is no good. It's misleading. It mixes up the whole point of the law. Writing this, it makes it look like a mass times some acceleration produces a force. But that's totally backwards. Acceleration is the outcome. Force produces acceleration. Mass resists acceleration. So writing Newton's second law like this just confuses the whole matter. Never write it like this. Written this way indicates what's really going on. And in vector form, we keep clear that it's forces causing acceleration. This is an input and the output. Input, output, right here. Okay, so there we have it, Newton's second law. And let us synthesize all that we've learned about dynamics so far with an example problem. So putting together dynamics concepts and skills thus far. This will be very important for you to work through step by step to check that you have understood what we've gone over so far. Here's the scenario. The intrepid Sir Isaac Newton is once again in outer space in his small rocket ship right here, but he is in peril. He's been gripped by the tentacle of a ravenous space squid that is pulling him. And oh yeah, there's also a black hole over in this direction threatening to pull Newton into that. You can't see a black hole because it's a black hole, you can't see them. So in the free body diagram for Newton at the moment, we see these three forces. A tension from the tentacle pulling him that way, a force of gravity from the black hole pulling him this way, and the thruster here that he's ignited is exerting a force upwards on Sir Isaac Newton. So we were going to call that an applied force upwards. I've given you the mass of Newton, 70 kilograms, and the magnitudes of each of these three forces. Each one is given in little k times big N, so that's kilonewtons right there. And you remember, of course, that little k, kilo, means thousand. So a kilonewton is 1,000 newtons. You'll have to convert those kilonewtons to newtons before you do any calculations with them. And I've also given you these two angles right here, the directions of those two forces. We don't have grid paper here, so we can't rely on counting grid spaces to figure out the numerical values of the components of these forces. You'll have to use good old trigonometry to calculate the x component of each force and the y component of each force. And that's the first task I would like you to do. Find the net force on Newton in the x direction and the net force on Newton in the y direction. Okay, the usual x, y axes over here. So start with just that part. Break these two forces into their x and y components using trig, and then sum up all the x components of the forces, sum up all the y components of the forces as well. Pause the video, do that now. I'll check in with you in a moment. Ready? Okay, let's see. If I want to sum the x components of the forces, I need fgx plus fax plus ftx. Fgx I can find using cosine of 30 degrees to get the x component. It's in the negative x direction, so I need a negative 50 kilonewtons times cosine 30 degrees. Fa has no x component, it's pointing straight up, and ft, down this way, I'm going to need cosine of 40 degrees to get its x component. So plus 70 kilonewtons cosine 40, it's in the positive x direction. Summing those, I get about 10.3 kilonewtons. I can leave this in kilonewtons for now because I'm just adding kilonewtons to kilonewtons. When we use Newton's second law in a moment, then I'll have to convert this from kilonewtons to newtons. Okay, likewise in the y direction here. Fgy, that is in the negative y direction, so a negative 50 newtons times sine of 30 to get that component. Fa is straight up in the positive y direction, 40 kilonewtons, and Fty down in the negative y direction, so negative 70 sine of 40 degrees to get this sum right here, negative 30 kilonewtons. So by looking at these two components, we can tell that the situation does not look good for Newton. Net force is down in the y direction and in the positive, down in the y direction, in the positive x direction, roughly towards our ravenous space squid. Let's draw that force vector to visualize exactly how dire the situation is. Here's our three original forces, and if we have negative 30 kilonewtons and about plus 10 kilonewtons in the x direction, then our net force is pointing something like that. Next steps will be to find Newton's acceleration. I want you to find the following: the x and y components of the acceleration, the magnitude of the acceleration, and then the direction of that acceleration. In particular, I want you to find this angle theta right here as a way of indicating the direction. So pause the video and use Newton's second law to do all three of these things. By the way, there's more than one way to do each of these things. I'll show you multiple methods for each one. Okay, pause the video, do 2, 3, and 4 here, and check in with me when you're done. Ready? Okay, number 2, the x and y components of the acceleration. That's exactly what Newton's second law is for. Here we've written it out in component form. Where's my component form? That right there, in component form, we took the net force x component divided by the mass of Newton, convert that from kilonewtons to newtons to get 147 meters per second squared approximately as the x component of acceleration. Likewise, for the y component of the acceleration, take the y component of the net force, that's negative, and convert that from kilonewtons to newtons, and we get negative 429 meters per second squared. Okay, now the magnitude of the acceleration. 2 ways to do that. By the way, pause the video if you haven't done this part already. Okay, here I go. Part 3, find the magnitude of the acceleration. Method 1, good old Pythagorean theorem. Since we have the x and y components of the acceleration, we can combine those to get the magnitude of the acceleration. Piece of cake. But you could also do this even without finding the x and y components of the acceleration. Since we had the x and y components of the net force, you could use Pythagoras to find the magnitude of the net force. And then use Newton's second law to compare the magnitude of the acceleration to the magnitude of the net force right here. Just divide that by the 70 kilogram mass of Newton to get, of course, the same result here and here. So 2 methods of finding that magnitude of acceleration depending on what information you have and what information you use. Okay, finding the direction here. A little trig helps out. Of course, remembering that opposite interior angles are congruent. You can see from this diagram that this angle right in here, that little angle is the same as this angle right there because these are opposite interior angles. So really I want to find this angle right there and make use of our knowledge that the acceleration of Newton will be parallel to the net force acting on Newton. And so this angle here is the same as this angle here, same as this angle, same as that angle. These are similar triangles for acceleration and net force. So I can find that angle by taking the arctangent of AY over AX and get about 71 degrees. Or another method, since they're the similar triangles, I could instead use the components of the net force. This theta is arctan of net force Y component over net force X component and get 71 degrees that way as well. Huzzah!